Um, Good afternoon, all, to our group colloquium. Today, we have a special guest and speaker from Rolls-Royce, Dr. Neil D'Souza. He is a technical specialist and expert in single crystal materials research. Dr. D'Souza completed his PhD in materials as well as postdoctoral position at Imperial College, London. And after completion of his PhD and postdoctoral research, he joined Rolls-Royce in 2001, initially worked in the area of the turbine blades manufacturing. Later, he joined in 2013 in the single crystal materials, especially nickel-based alloys, and he became the technical specialist in that area. Has more than 80 journal articles, as well as he has also holds 5 patent applications. Um, Dr. D'Souza also collaborated with various universities and institutes in UK. Today, he is going to present an overview of the research, especially in the turbine materials at Rolls-Royce. Dr. D'Souza, thank you very much for accepting our invitation, and I would like to present your talk now. Thank you.
Okay, thanks, Prakash. I'll just get this into presenter mode.
Yeah.
Yeah, I presume this is sharing. I think it should be.
Yeah.
Okay, good. So, so at the start, thank you. Like I said, thank you very much for inviting me to present at this colloquium. My aim is to just kind of give a very broad overview of the work we do, and more specifically, I kind of present two topics very briefly. I mean, more from the point of view of giving an overview rather than anything else. Most of that work has been published, so the references are available if you wish to see more of it. Again, at the outset, I would like to acknowledge a lot of the people who have collaborated on these two specific topics. So they range from folk at NPL as well as a number of UK universities. I have collaborated extensively with Jeff, on one of these topics and amongst many other topics, and also Carl, who I didn't know would be on this call. So yeah, we have worked again together, Carl, myself, and Jeff on disc alloys, and also some of my colleagues at Rolls-Royce. So the list is not definitive, but like I said, these are one of the principal people who have been quite actively involved in the two topics that I want to present very briefly today. If you need to ask any questions, I mean, I'm quite happy for you to to ask them in between. There's no, I don't see any need for me to finish for you to ask. So if you need to ask anything, by all means, don't stop to ask the question.
Sorry, guys, are you sharing any slides? Sorry, I can't see anything.
Oh, okay. Interesting point. Okay, I should be.
Is that a problem only for me, or?
No, I can't see any either.
Oh, okay, so let me reshare it then. Okay, I think. I presume this is sharing now?
There we go. Yeah.
Oh, yeah. Perfect. So let me just go to just. So is this the sharing?
Yeah.
Okay, yeah. Perfect. Thank you. Okay. So first couple of slides, I just want to give a kind of overview of what Rolls-Royce is. Like I say, this is far from the this is far from being definitive. It's just a kind of very overarching distribution of functions. As you know, we keep chopping and changing. So this is as of now. So very briefly, Rolls-Royce PLC is divided into 3 sectors. So it's civil, defense, and power systems. And probably it's important to state that it's a global company. So even though it's kind of headquartered in the UK. It really is a global company with branches in the US, in Germany. We've got uh, a repair outfit up in Singapore, in Bangalore, and also a foundry in China as well as in Italy. So it's truly a global company. We are split functionally into three main groups. So it's civil, defense, and power systems. Civil is the major business of the company, and it's mainly centered in Derby. So Derby is primarily civil, and civil itself is comprised of a number of units. Very briefly, we call them 7 units. So we've got customers, services, product development and technology, business aviation. Business aviation is mainly looking at aircrafts, not so much for civil large, not mainly for, like, for example, commercial airlines, but more for business jets. And then you've got operations, and you've got digital, and you've got IT. So kind of 7 main functions within the civil aerospace primary function. Defense is a smaller business. It's primarily based in Bristol, up in Filton. It's just exactly kind of opposite to where BAE Systems is located. We've also got North America, Rolls-Royce North America, which again is heavily defense oriented, and the nuclear business up in Derby, up mainly on the A52, not too far off from where we are, up in Sinfin. It's more kind of Rainsway. That's mainly the nuclear business. So nuclear now sits ensconced within the defense business. Power systems is based in Germany. So that's Rolls-Royce Deutschland. So these are the 3 main, kind of primary business units that constitute Rolls-Royce. Now, I did mention that, within civil aerospace, we've got operations. I mean, we've got operations, product development, and technology and services. These are contained within aerospace, and in many ways, these kind of form one of the principal constituents to which materials as a function contributes towards. So if you look at operations basically comprises of, as the name suggests, it's comprised of some supply chain units. Primarily, these are the supply chain units that produce the components towards the engine. So as you would imagine, you've got turbines. There's another that exclusively makes vanes and nozzle guide vanes, seal segments, turbine blades, and so on. Then you've got rotatives, which makes critical parts like discs. Then you've got compressors, and you've got installations. We used to historically have more of these supply chain units, but over a period of time, some of them have got amalgamated. So now, as it stands, currently we've got 4 consolidated supply chain units. Now, the 2 main functions that in a way kind of service Rolls-Royce are materials and manufacturing. So operations, etc., they make parts, but in many ways they are supported by the materials function as well as the manufacturing function. The materials function in Derby. So historically in materials, we used to be a central function, but over the last, I think, 4 or 5 years, we have become more civil centric. There is an equivalent materials function that services defense in Bristol and in the US. But effectively, the materials function that I work in and many of my colleagues do, we come under PD&T as is referred to, and effectively in PD&T, that's product development and technology, we support both operations, which is effectively the part of the business that makes components for the engine, and also services. Now, services is a very big part of the organization, simply because when you make an engine and you sell it, that's just a small cost. But services effectively is when you constantly replace parts and you produce new parts and you service the engine. So we make a lot of money through services. And services is a business that is kept on growing over the years, and currently it contributes a great deal to the company's revenue. So materials effectively supports both operations as well as services. The manufacturing function is a function that pretty exclusively supports the operations part of the business, but it also is comprised of a central in addition to having manufacturing engineers who are based within plants. It also comprises of a central function, a bit like materials, and they sit in a kind of central function which is called as the innovation hub. Again, this is something that has been created more recently, but effectively, these are a group of people sitting in a more centralized location and deal with at the same time with all different parts of the operations, as opposed to the operation manufacturing engineers who sit exclusively within an SCU. So this is kind of roughly what the materials and the manufacturing functions are and how they support the bigger business. So going down more towards materials, because that's effectively where we sit. Materials, like I said, historically used to be a central function. Now it's kind of subdivided into civil and defense. So within the civil aerospace business, the materials function pretty much exclusively sits in Derby. And within the function in Derby, we're about 100 odd people. We are broadly split into 4 main groups. There's a high temperature group, which effectively comprises of people working in disc alloys, turbine aerofoil materials. We in turn service, the turbines and rotatives SCU. We also support failure investigation, of the fleet. And in addition, it also contributes to additive manufacturing, which is specifically used for repair. And that in turn forms a major constituent of the services business. Then there is a group that works on titanium and steels. So again, servicing the compressors and the installations part of the supply chain unit or the SCUs. Then there's the process modeling and joining team. They not only provide process modeling support to all the SCUs, but also there are a group of materials engineers who support rotatives, because that's one of the main regions where joining forms an integral part of the function. And then there's a surface engineering group. This is again a very important group because practically every single turbine component is coated. You never ever have a uncoated turbine component, simply because at those kind of operating temperatures, you would see corrosion and you would see oxidation. So you need to provide some kind of protective coating to the blade or the vane or the segment. So you've got a surface engineering group that deals a lot with coatings and bond coats. So basically TBCs, bond coats. They look at tribology, and also sitting within that group is a non-metallics group. Now, non-metallics is not a very big part of the function. It's not a very big part of the materials organization, but it still is a sizable contribution, and specifically these days when hybrid and electrics are contributing to a major role within the engine. So the non-metallics group that looks at kind of non-metallic constituents sits within the surface engineering group. So with that backdrop, what I wanted to just kind of next show is I did mention of the 4 groups within that reside within materials. So the next question is, how is that cut in terms of the type of materials that we use within a, say, for example, a civil large engine, an engine used for the A380 or the A330 or the A350. So very, very broadly, if you look at a general arrangement diagram, that's how broadly an engine looks as you traverse from the fan all the way to the hot part of the turbine. And as you would see, there's a wide range of materials used within the engine architecture, which is dictated by the maximum operating temperature of that part of the engine, as well as the key mechanical property requirements or the oxidation requirements that are needed, for a component to satisfy. So very broadly, what you'll immediately see is that the hottest part of the engine, which is effectively the turbine, is primarily comprised of nickel, and also the compressor, which compresses air that then expands into the turbine and provides you the power for the lift, is also quite exclusively comprised of nickel. Then you've got the colder parts of the engine, as you come closer towards the fan, etc., which can be titanium. They can be titanium. More recently, they're composite materials. So the A350 fan blade is no more metallic. It's a composite white cord material. So again, that's your non-metallics. And then of course you've got steels, which effectively form the shafts that that are used in the different stages. So very broadly, what you would see is that it's primarily metallic. It's almost 95% metallic. And at the same time, you have a sizable amount of this, which is kind of primarily nickel. And this nickel effectively forms the high temperature materials group, which myself and a few others form a part of. Now, within the materials that you use, you can use different technologies, to form these components. And the technologies that you use, all of that is used in the different operating business units. So, for example, turbines, rotatives, installations, and compressors. So if you look closer to home, as far as we're concerned, if you look at within the turbine, then you get the discs, which is the critical part of the engine. So for discs, you will primarily use a forging or a thermo-mechanical operation to produce the discs. If you look at, for example, combustor cassettes, or in some cases, some blades, you might use an additive kind of manufacturing route. So be it laser powder bed. In terms of repair, you might use you may use a DED, the direct energy deposition method. And for blades and vanes and segments, which is something which I'll, at least one of the topics that I'll kind of share with you, is we use investment casting. Which is again one of the state-of-the-art methods for the manufacture of turbine blades. So within the engine, there are a wide range of materials, and across a wide range of materials, you also have a wide range of manufacturing processes. And in many ways, the manufacturing processes and the materials are interlinked. So if you got a particular material, it would need you to manufacture it in a certain way and not in another way, because a lot of it is governed by the strength of the material, the ductility, and so on and so forth. So anyway, you'll see more of this as we go along. So the main intent of this slide is to give you an overview from the perspective of what drives basic materials research. So if you look at the materials function, be it nickel or be it titanium or whatever, the basic concept is, what are the two main driving features that effectively makes us work towards a particular routine? So you can probably so if you look at, for example, a turbine or the hottest part of the engine, you could very broadly say that there are two main routes that one can adopt for developing a material of a higher temperature capability. One of them is, of course, you develop a material which has, so in other words, you develop an alloy. You can go from alloy A to alloy B to alloy C. Each alloy that you develop, you alter the chemical composition, you change certain elements, depending on the properties that you want. So, you want to increase the strength, or do you want to increase the oxidation performance? Do you want to increase the wear characteristics, and so on and so forth? So that's kind of dictated by development of substrate materials. And when I say substrate, what I basically mean is the alloy. So, which alloy do you use? Another very important stream of work, which is becoming increasingly important these days, is how do you effectively reduce a metal temperature? So the temperature of the gas stream, so typically for an HP turbine, the temperature of the gas stream is about 1,600 degrees. Now, you would not have many metals, or at least the common metals that you use, that would be able to survive at those temperatures. I mean, leave alone nickel. So how do you effectively cool the blade? How do you make the temperature of the blade colder, even though it's in contact with a very hot gas? So two very common ways of doing this. One of them is to provide for internal cooling passages within the blade. So you may pass air, through different cooling channels within the blade. So effectively, it serves to cool the blade. It takes away the heat. So clearly, you need to have some kind of cooling arrangements within the blade. Another more effective, well, an equally effective way is if you deposit a ceramic on the surface of the blade. So effectively, you put a layer on the blade, like a coating or a thermal barrier coating, which has got a very low thermal conductivity. So if you remember, what I said was one of the groups in materials actually looks at thermal barrier coatings, or the surface engineering group. So roughly, you've got two methods by which you can develop materials. One of them is, for a given material, you can have, more, you can either go down the coating route, or you can have more intricate methods of cooling, which again is linked to the manufacturing process. And the other aspect is, well, you just end up developing an alloy which is stronger, or which is more higher melting. So that's the kind of, very broad brush way in which you can develop alloys, for increasing the temperature capability. So if you look at the alloys that that one can use to develop the temperature capability, and looking at nickel base alloys. So now we're looking at the turbine, we're looking at nickel base alloys. You can track the evolution of these alloys roughly over 4 generations. Now, again, I'm just mainly focusing on single crystal alloys. If you look at the whole gamut of nickel base alloys, you can start off with equiaxed alloys and then directionally solidified alloys, both of them being polycrystalline, and then single crystal. But practically every component in the turbine, apart from the LP, is LP being low pressure, is single crystal. So the onus will be now on single crystal. So if you look at the evolution of single crystal alloys from the point of view of temperature capability of substrate materials, it kind of spans 4 generations. The first generation, roughly, you would say in the early 80s. The fourth generation, pretty much the late 2010, it's around after 2010. So when you go from the polycrystalline alloys to the first generation single crystal alloys, the main difference is in the addition of a refractory alloying element like tantalum. And these first generation nickel based alloys have got tantalum added to them. The main reason being tantalum is a solid solution strengthener. So it basically makes the alloy, the gamma phase or the matrix phase of these alloys quite strong. So the main difference between earlier alloys or polycrystalline alloys and the first generation single crystal alloys is the addition of tantalum as a solid solution strengthener or as a refractory metal. When you go from the first generation alloys to second generation alloys, and that typically happened in the early 90s, the big difference between first and second generation is the addition of rhenium. Rhenium is one of the main elements added to second generation alloys. Again, the reason for adding rhenium is you want to make it stronger, even more stronger than the first generation alloy. So the main reason from going from 1 to 2 is to increase the strength. And one of the ways you can increase the strength is by the addition of rhenium. Now, the important thing to note is that rhenium is not an element that occurs in abundance in the Earth's crust. Actually, it's a byproduct of copper. So I don't know it off the top of my head, but for several tons of copper, you might just get a few grams or a few kilograms of rhenium. So rhenium is a pretty expensive metal because the amount you can claim for a given amount of copper is quite small. So whilst it's an important element that's added in second generation alloys for strength, it comes at the cost of sustainability and comes at a cost and it comes at cost. So second generation alloys are markedly more expensive than first generation alloys. Then you go to third generation alloys. Third generation alloys, again, the only difference between them and second generation alloys is increasing amount of rhenium. So going from 0% rhenium to about 3% rhenium, you go to about 6% rhenium. So third generation alloys, again, the reason from going from second to third again is because you want to have stronger alloys. You want to have alloys which are more capable of creep, specifically in parts of the turbine, like the IP blade, which you don't generally cool. So those blades are generally more hotter because the metal is running at a higher temperature, and therefore you want the blade not to have poor creep properties. So one of the main reasons of adding an added amount of rhenium is effectively to increase the creep strength. So therefore, the difference between second and third generation alloys is the addition of rhenium. There's also some amount of tantalum added, but you might argue that they're not very different. They're more or less the same. So it's primarily the amount of rhenium. Now, the problem with increasing amount of rhenium that you add from first to second to third generation alloys, it's got two problems. The first problem is as you add rhenium, you increase the instability of this alloy. So basically, if you operate this alloy at a high temperature, say around 1000 degrees, for several hundreds of hours, you end up forming you form unfavorable phases which are detrimental, like for example, tetraclinary close pack phases, or commonly called as TCP phases. So third generation alloys are good in terms of strength, but their strength will deteriorate over a period of time because of the added amount of rhenium. The other problem also with third generation alloys is they are they're poorer in oxidation compared to second generation alloys. So clearly you need to coat them. But one of the ways of overcoming the drawback of them being unstable is by lowering the amount of chromium. So if you see, if you look at third generation nickel-based alloys, whilst they have higher rhenium, they generally will have lower chromium. The lower chromium is done is done primarily because you want to not lose the strength of this alloy over a protracted period of time because of these TCP phases. But the moment you decrease the amount of chromium, you simultaneously decrease the corrosion resistance and the oxidation resistance. So generally speaking, third generation alloys are poorer in oxidation resistance compared to second generation alloys. So one of the ways of overcoming the drawbacks of third generation alloys was in the creation of fourth generation alloys. So fourth generation alloys, again, the major difference is now it is in the addition of ruthenium. And one of the main reasons for adding ruthenium is you can slightly decrease the amount of rhenium, but even for that amount of rhenium, the presence of ruthenium stabilizes the alloy. So the tendency for you to form TCP type phases is diminished. So it's possible for you to slightly increase the amount of chromium and therefore not lose out on the oxidation compared to what you would have lost in a third generation alloy. And at the same time, the alloy is also retains its strength. So whilst you can recover your instability, or in other words, make it less unstable, you do also get some increase in the amount of oxidation performance. But the point is you're adding ruthenium. Now, if you think that rhenium was an expensive element in its own right, ruthenium is a lot more expensive. So again, fourth generation alloys are extremely expensive. And just to give you kind of magnitude for cost, I mean, this was going way back about 10 years ago. The cost per kilo of, for example, a third generation alloys was of the order of a few £100. It was nearly 8 times more expensive if you use TMS 138A, which is a Japanese alloy. So the long and the short is fourth generation alloys have now been discontinued. One of the main reasons being cost. The implications of cost are too strong, to counteract anything in terms of the life of the blade. So in Rolls-Royce, our general route is that we use CMSX4 as our second generation alloy, and we use RR3000 or RR3010 as a third generation alloy. We use little to none of any of the other alloys. So the next thing is looking towards the method of manufacture. So like I said, materials and manufacturing in a way go hand in hand, because very often the material that you make will dictate the method of manufacture. So as far as turbine blades are concerned, the method of manufacture is investment casting. And there are two main reasons for this. So like I said before, if you want to make a polycrystalline disc, well, in that case, you would use forging. So the question is, why can't you use a thermo-mechanical route to make a turbine blade? The answer is very simple. Turbine blade alloys are a lot more stronger, simply because the typical operating temperature of a turbine blade is roughly about 900 to about 1000 degrees, maybe 1050. The operating temperature of a disc is about 650 to about 700 degrees, 700 to 800 degrees. So clearly you've got about a 400 Kelvin, deficit in temperature that a disc is meant to operate at compared to a blade. So blade alloys are definitely more stronger. So the stronger the alloy, the more harder it is for you to thermomechanically process it. So therefore, that immediately cuts out the forging route altogether. The other thing, if you remember, I did mention was, when you look at how do you develop alloys for higher temperature capability, one of the ways is to put complicated cooling passages. So you cool the blade, you either put a TBC, or alternatively, you have internal cooling passages where you flow air. Now, such kind of intricate cooling passages cannot be produced by any other method apart from investment casting. So again, go back to the same old point, rather than me sounding as a broken record, is that the method of manufacture and the temperature capability of the material in many ways dictates the method of manufacture of that component. So for turbine components or turbine blade components or turbine vanes, the method of manufacture is investment casting. Now, investment casting is nothing new. It's a process that operated in Mesopotamia way back in 3000 BC. It's also called a lost wax process. So all that we're doing is actually using what was invented by man a few thousands of years ago to create components which are of the order of at least a few £100 by the time they're made. So typical turbine blade, by the time it's made from the wax stage to the time it's been heat treated, goes from a few tens of pounds to almost about £500. And hence the word investment casting. So investment casting broadly comprises of a number of stages. I don't want to do, go into too much of detail, but it suffices to state you start off with a wax component, so that it's a wax replica of the blade that you want to make. Like I said, these blades are not solid, they're hollow because you've got complicated cooling passages. So to produce the cooling passage, you have a core. This core exists within the wax. So what you normally do is you have a wax pattern die, you place the core in the wax pattern die and you inject wax around the core. And effectively you get a wax pattern like you see there, but it's got an internal cooling passage given by the shape of this core. So effectively it's a composite between a wax and a core. You assemble a number of these wax patterns on a carousel. The point to make again is that you don't produce one component at a time because it's clearly not cost effective. You produce a number of components at a time, so therefore you align a number of such wax components on a on the base of a wax pattern. You then apply ceramic coating or shell around it. It's typically about 7 coats. And typically the thickness of the shell could be of the order of 5 to 7 millimeters. It comprises of a number of layers. The layer in contact with the metal that's going to be poured into it has a slightly different composition from the backup layers, which are important to give the strength and rigidity to the mold. So you produce a mold, which effectively is ceramic shell that is that encapsulates the wax. Then once you form the mold, you effectively then effectively what you do is you burn off the wax, because effectively you want to now produce a hollow cavity into which you pour the metal into. So you put these ceramic molds into a boiler valve, and under pressure you effectively burn out the wax. So all that remains now is the ceramic shell with the core in between. And the gap between the ceramic shell and the core is effectively empty, and that's the region into where you pour the metal into. Then once you have burnt off the wax, you pre-fire the molds just to basically strengthen them. So in other words, a bit of sintering, because these are kind of green in this condition. And then you basically you form the mold. You then pour metal from the top of the mold that fills up these cavities, and that's the end of the casting process. But remember, when you finish the casting process, you've got metal, but you've also got this core in between. So you don't have any hollow cavity to begin with. So what do? You then use, you use either sodium hydroxide or potassium hydroxide under pressure, and which is in the boiling form. And effectively, what it does is the potassium hydroxide or the sodium hydroxide effectively leaches out the ceramic. And what you're then left with is a blade which has got the solid metal with a hole or a cavity which is now been removed because this core has been leached out. Now this blade is in the cast condition, and as you would know, casting is one of the major drawbacks of casting is you end up with segregation, simply because the solubility limits of an element in the liquid and the solid is not the same. Some elements segregate to the liquid, some to the solid, and in the nickel-based alloys that we use, elements like rhenium, tantalum, etc., chromium, they've got very strong segregation tendency. So you've got a lot of micro segregation that exists across a casting. So you have a subsequent heat treatment process, which involves 3 stages. which is, a solutioning stage for homogeneity and a primary and a secondary aging to effectively produce the blade in the condition that you can then use in an engine. So that's really, kind of overview of what the manufacturing processes are. So the next question is, okay, you've got a turbine blade. So say in this case, you've got a turbine blade, which typically looks like this. So you've got an aerofoil. This is more like an HP turbine blade. So it's got a short aerofoil. It's got a root block. It's got a platform, and then it's got a fir tree. So we call this a fir tree because it looks like a fir tree, and this is where this blade gets inserted into the disc. But as you would immediately see, you've got the internals of this blade have got cooling passages like you saw in the previous slide, but also you get these sharp radii of curvature, where the aerofoil blends onto the platform. Now, these internal cooling passages, as well as these very sharp radii of curvature, they are regions where potentially you can have stress concentrations or plastic strain that develops. So remember, when you cast, you actually you're casting metal around a ceramic, and both the metal and the ceramic do not have the same coefficient of thermal expansion. So you've got a thermal fight that exists between the metal and the ceramic in these internal cooling passages. At the same time, you got very sharp fillet radii where the turbine aerofoil blends with the platform. So potentially you've got regions in the casting where you can get stress or plastic strain that develops during casting. Now, all that is fine in the casting. You've got plastic strain. So what? As far as the casting is concerned, that doesn't cause any harm or any detriment. But like I said, because the casting is heavily segregated, you need to homogenize it, and the typical homogeneity is at very high temperatures. So if you look at, like I said, we use CMSX4 and RR3010 or RR3000. So the typical solutioning or homogenization temperatures vary between 1310 to 1360 depending on the alloy. And the typical isothermal hold at these temperatures could be anything between 5 to 20 hours. So what happens is when you have a pre-existing plastic strain beyond a certain value, which is equivalent to a certain dislocation density, you've got high strain energy within these regions. And during homogenization at these temperatures, which has been done primarily to remove the segregation, you have another effect that happens. You have recovery followed by recrystallization. So while on the one hand, you're trying to homogenize the microstructure to get a segregation-free casting, at the same time, what you're also doing in regions where you've got high plastic strain, you're producing recrystallization. Now, this is something you definitely do not want in a single crystal alloy, because in a single crystal alloy, you do not have grain boundary strengtheners. And therefore, if you do have a grain boundary, which is a random high angle grain boundary in the case of a recrystallized grain, you have a dramatic drop in strength. And because of this dramatic drop in strength, you clearly cannot accept this blade in service. So typically, you can see this is a portion of a heat-treated IP turbine blade. So it's got, unlike in the case of an HP blade, the IP blade has a longer aerofoil, and you can see in the region around this sharp fillet, you've got this recrystallized grain, which is also about maybe of the order of a couple of millimeters. So this blade then immediately gets scrapped. And the cost of this blade at the time it reaches heat treatment is of the order of at least about 300 to 400 pounds. So you can imagine the amount of non-conformance you could get through heat treatment if you have a component where you've got a high degree of plastic strain. So it's important for us to understand, or to define the critical conditions where these recrystallized grains form, but also at the same time, we should be able to model these. So modeling is a key, like I said, the process modeling group exists in Rolls-Royce, and one of the key jobs of the process modeling group is to model such kind of defects such that you can engineer around it and effectively not have high non-conformance. So modeling of the evolution of plastic strain during high temperature freezing of a turbine blade is quite important. One of the main reasons being, it relates to the role of recrystallization. But whilst this may seem reasonably straightforward, it is far from straightforward. And one of the main reasons being that any model is only as accurate as the data that you basically supply to it. So if you look at typical models that people generally do run, which are run at lower temperatures, typically about say 1100 or 1000 degrees, there's a lot of reliable data that exists in literature as well as our own measurements, and models are reasonably accurate. But when you come to high temperatures, typically of the order of about 1300, data is very scarce, is very scarce. And again, the ones that do exist have, I mean, at the very best, you could probably say that they are less reliable than what you think they could be. So one of the things that we set out to do very earlier on is to produce a set of experiments where we mimic the kind of conditions that occur during the casting of a turbine component. And under those conditions, try to measure what the creep performance of the metal would be as an input to the mechanical model that the process modeling team would run. Now, as far as investment casting and cooling of a turbine blade, if you want to look at modeling the creeps, modeling the creep strains that develop, there are two important criteria. Now, the reason why I say creep is because at temperatures of the order of about 1300, you have got very limited amount of hardening. The material is extremely plastic, and therefore it flows very easily. So therefore, creep is one of the main mechanisms by which you get deformation at such high temperatures. At lower temperatures, where recrystallization is not that important in terms of the evolution of stress and strain, hardening becomes more important. But at higher temperatures, creep is one of the main deformation mechanisms. So you need to be able to produce a model, or you should be able to produce a set of experiments to get you some data, but that looks at some of the key aspects that relates to creep under these conditions. So in terms of investment casting, there are two very important aspects that one needs to consider. The first thing is the occurrence of creep, but this is more like non-isothermal creep, because remember the material is constantly cooling. So a traditional creep test, you take you take your specimen, heat it to a certain temperature, and hold it at that temperature for several hundred hours. That's not the creep that we have here. In this case, the metal is constantly cooling. So if at any point in time, it's only sitting at that temperature for a few seconds. So there's a non-isothermal creep aspect. The other important aspect is history dependence. So if you look at a classic thermodynamical function, like say, for example, Gibbs free energy or enthalpy or whatever, which are state functions, it's not important. The change in the enthalpy or the change in the Gibbs free energy is not dependent on the path. It's only dependent on the initial and the final stage. But deformation is not a state function. The deformation at a certain temperature during cooling is dependent on the prior deformation at a higher temperature from which the metal cooled. So in other words, if I'm cooling something from say 1400 to 1300, then the deformation at 1400 will dictate the deformation at 1300. So in other words, there must be some history dependence of deformation in terms of investment casting. So this is not typical simple creep experiments that one would do, isothermally, because in many ways, there is a path dependence of deformation that influences the evolution of creep and strain, that influences the evolution of creep and plastic strain at lower temperatures. So very simplistically, what we say is, okay, the strain is partitioned classically into the thermal strain, the elastic strain, and the plastic strain. The plastic strain is essentially comprised of the hardening strain and the creep strain. And what we want to do is we want to find some expressions or some constitutive laws by which we can get expressions for the hardening and the creep versions of the strain under typical investment casting conditions, which reflect A and B. And like I said, one of the main drawbacks is that there is no pre-existing data that exists. So pretty much, the data that we've produced is the one that that probably I would say is by far the most reliable, because there is no pre-existing data that I've at least come across in such kind of conditions. So what we set out to do was to develop constitutional equations that mimic hardening and creep that can be used for process modeling in the calculation of plastic strain under conditions where you get investment casting influencing recrystallization. So what we really do in these experiments is we take a specimen, we heat it to a certain temperature, we cool it down to a certain temperature, and at that temperature we do a very short-term creep test. And at the end of the creep test, we cool the specimen down and effectively do a series of these tests at a given cooling rate, but for a series of different temperatures. So this is an example of one such test. You can do the same test at a number of temperatures. So in other words, at 1300, at 1280, at 1270, at 1250. So effectively what we did was we did a number of creep tests for a given cooling rate to cover a temperature range between 1300 to 1150, typically the kind of temperature range where creep is important, and creep is important from the point of view of recrystallization. So we did this using miniature testing. One of the main advantages of using miniature testing is because you can look at the compositional effects of as-cast microstructures. So one of the things to bear in mind is that miniature tests, the specimens are extremely narrow. So they're just typically 2 by 1 in terms of cross section, much smaller compared to your traditional macro specimen, where the typical gauge diameter is of the order of about 6 millimeters. You've got a parabolic temperature profile across the length of the specimen. But the most important thing here is because the cross-section of the specimen is quite small, in many ways it is of the same order of length as the thickness of the cooling passages in a turbine blade. So if you look at a typical turbine blade and you look at the cooling passages, a typical metal thickness around the cooling passage is of the order of about maybe a millimeter or a millimeter and a half. So by using miniature testing, where the gauge dimensions are typically of the order of the thickness of the metallic passages in a turbine blade, in many ways you're able to capture the right length scale and also take into account the fact that in an as-cast microstructure you've got a range in segregation, and therefore in many ways you're able to capture not only the effect of the of the specimen cooling passages, but also the fact that different regions can have different amount of segregation. So in this miniature testing type of method, you do not measure the plastic strain using extensometry, because clearly you cannot pin an extensometer on such very thin cross sections. Rather, you measure the plastic strain indirectly through resistance, because as the material plastically strains either in tension or compression, the resistance changes, and therefore by using the resistance, you can then calculate the plastic strain. So clearly we do not have extensometry in such kind of experiments. We use a typical cooling rate, which is akin to the cooling rate that one uses in investment casting. And like I said, these are non-isothermal creep tests, but they're isothermal for typically of the order of 800 seconds. So traditionally you would call them non-isothermal because they are very different from a traditional creep test that will run for several tens of hours at a given temperature. In this case, they're at best isothermal for about 10 minutes. So I would say that they're isothermal creep tests, but for about 800 seconds. But if you want to look at it in terms of a traditional creep test, well, you can call them to be non-isothermal. The main aim in all of these was to produce an expression of this nature. The reason for having an expression of this nature is because this is an expression that is quite easily handled by abacus or by procast. All that you need in a procast or in an abacus model are values of the damping parameter, the pseudo activation energy, the backstress term, and the value of n. Now, it would be very useful if in our constitutive equation, we can get eta, q, sigma naught, and n relatively constant or independent of temperature. Now, it fortuitously happens to be the case. The value of n, the value of q, and the value of eta are independent of temperature. The value of sigma naught, of course, will depend on temperature. Sigma naught is the back stress. So effectively, if you got dislocations piling up at an obstacle, with increasing amount of time as the number of dislocations pile up, sigma naught becomes, changes. So when there's no obstacles, sigma naught is 0. And as the number of obstacles increases, sigma naught increases. So from the point of view of investment casting or cooling, initially when you have cooling at high temperatures, when you have a single phase, sigma naught is 0 because you've got no precipitates. The precipitates are the main reasons why you get hardening. Remember, we don't have grain boundaries here, so the only form of hardening arises from precipitation. So as long as you don't have precipitation, you can take sigma naught equal to 0, or there's no backstress term. The moment you get precipitation that occurs typically in this temperature range, sigma naught begins to become non-zero. And not only is it a function of stress, it's also a function of temperature. So we've got a very nice expression which can be used in any mechanical model that can estimate the amount of creep that occurs. Now, this is very useful, but the first question is, how does it compare to experimentally measured creep data? Well, the fit's not too bad. You can clearly see that there's a reasonably good fit between the experimentally measured creep data as well as the constitutive equation that we have derived based on least squares. So one of the principal applications, that we've used miniature testing is in the development of a constitutive equation for creep. And this is an equation that, the process modeling people within Rolls-Royce can use to model the evolution of plastic strain and stress in the prediction of recrystallization. The second example I want to give you is something which is slightly different. This is more from the point of view of repair. So like I said, repair is another very important part of the business, simply because repair is the part of the business that basically feeds into services, and services is a very big part of the organization, where a lot of our money is generated by putting repaired components back into service rather than just basically scrapping them. So the example in question in this case is using, is that of a segment. So seal segments are typically components that are static. So these do not rotate like turbine blades. And really what the main function of a seal segment is that the seal segment has got an abradable. So if you see a schematic diagram that I have here, this whole structure is the segment, and this is a blade. So the blade actually kind of extends further down, but these two protuberances are the tips or the edges of the turbine blade. So these blade fins cut into the abradable. So this is one abradable, that's the other abradable, and these blade fins cut a track in the abradable as this blade begins to rotate. So while the segment is stable, is non-rotating, the blades are rotating, and as they rotate, they cut a track into the abradable. So the main function of the segment is to allow the blade to cut tracks within the abradable such that you do not have any air tip leakage. If you have any air tip leakage, effectively you end up having performance losses. Now, what happens is at the end of a certain number of cycles of the engine, what actually happens is that the segment as a whole is fine. There's no problem. I mean, there's a bit of wear, but it's still acceptable for it to go back into the engine a second time. But what really happens is that the abradable, because it's been constantly cut by these blade fins, is actually worn out. And what historically you would do is you would actually bin this entire abradable. Well, you would bin this entire segment just because this little abradable there and this little abradable here has been worn out. Now that's a real colossal waste of money, because you could still use the entire segment, put it back into the engine a second time around if you just repaired these abradables. So that's exactly what we do. So when the segment comes back from service, you remove these abradables, you kind of mill them out, but then you rebuild them back, and you rebuild them back using an additive layer process. So effectively, you take away the worn abradable, you rebuild these abradables back, and the whole segment goes back again into the engine, and you get a tremendous cost advantage. So typically the cost of this entire repair process is aimed to be less than 60%, or is aimed to be less than 60% of the cost of the OE segment. So automatically you've got massive cost saving. So this is an example. You've got a segment here. You've used a you use a nozzle to deposit powder, through the nozzle, and you've kind of built up this this support structure. So clearly you see the support structure has been built up already on this surface, and it's in the midst of being built up on that surface. So this part of the surface has not yet been built. It's been built here, and as this nozzle keeps moving and translating, you'll end up building the abradable structure on that surface. So the most important thing here is that, okay, you've built up, you've repaired the existing abradable with a new abradable. Can you now qualify the mechanical integrity of this abradable such that you do not have any form of deficit in properties compared to the OE condition? So if you look at this abradable in plan view, and that's what I call as the OEM. So that's the unrepaired condition. What you have is you get a kind of a nodal structure. So you get these, kind of crisscross structures. You got nodes along the length of the abradable wall, and you've got internal nodes, or we call them, X nodes because they resemble an X, and you've got K nodes, which are the nodes along the length of the wall. Now, the thing to keep in mind here is that when you put this segment into service, so when you put this segment into service, you've got an abradable there, you've got an abradable here. This segment actually operates in a temperature gradient. So the portion of the segment which has got the abradables, or this portion of the segment, is hot because it's in contact with the hot gases, whereas the back of the segment, which is where we got the hook, is cold. So you've got a thermal gradient that exists across the across the segment. So therefore, in service, what really happens is this segment begins to flatten. So you get some kind of flattening and unflattening over the course of the service life of the segment. And because of this flattening and unflattening that occurs, you get residual stresses that build up within the abradable, because keep in mind the fact that this abradable now has been additively built. So in addition to the pre-existing stresses that would have existed after you build it, you additionally get some stresses that are going to form because of this thermal flattening and unflattening in service. So one of the important things that we want to ascertain in this repair project is we have a pre-existing design of the abradable, which is this kind of nodal design. Number one, is it possible for us to develop an alternative design such that the residual stresses both during build as well as during service are lesser, which would mean that the abradable will have a longer life on the segment? And if that is the case, how do we actually approach this? I mean, what kind of tests do we need to do to assess to assess different designs? Now, it's not straightforward to do any form of diffraction based work, etc., to look at residual stresses, because these materials are highly textured and they're not entirely metallic, because you've got a metallic support structure, but in between the metallic support structure, you've got a sinter filler, which is, say, nickel aluminide, which also gets basically oxidized. So we must find a test that we can use quite reliably to qualify different support structure designs. Now, the point to note here is that during service, this segment flattens and unflattens. So one of the ways in which you can define a criterion is by looking at the elastic modulus. So if you look at the elastic modulus of this abradable in out of plane flexure, because it's clearly flexing in and out of plane, then that may be a very useful test in ascertaining whether it's possible to go from, say, a nodal design to a non-nodal design in order to increase the length or increase the life of this abradable. So that's exactly what we did. We deposited abradables of two different designs. One was the repaired nodal design, where you still had the same design as the OE condition. The only difference between the two being this is being repaired as compared to this being initially single crystal. The other design that we looked at was a non-nodal design. So effectively you had these loops. So clearly you do not have any K nodes or the nodes that exist along the length of the abradable. At the same time, you do not have any internal X nodes. So these are two, this design was radically different to this design. And the question is, how do they perform in out of plane flexure? So again, we used a typical ASTM type of test. We used resonance methods to determine the elastic modulus of this composite structure. So you use impact excitation, based on ASTM 18E1876 the the basic flexural nodes or the F1, F2, F3 nodes, etc. in resonance, and from that you can then calculate the effective through thickness elastic modulus of the nodal as well as a non-nodal support structure. So these are examples of examples of the graphs that we got. So if you look at the nodal design, you see a typical case where the elastic modulus decreases. So when I say elastic modulus, is the effective elastic modulus, not the elastic modulus per se of a metallic system, because this is really a composite between a metal and the oxides that are packed in between the interstices. Whereas if you look at the non-nodal design or the continuous path or the squiggles, you see an interesting aspect. The most interesting aspect you see here is that the non-nodal support structure has a lower elastic modulus than the nodal design. So therefore, in service, when you're constantly flexing the abradable, in out of plane flexure, if you got a lower elastic modulus in the non-nodal design, it'll certainly have a longer life compared to the nodal design. And if you looked at the elastic modulus in out of plane flexure in the unoxidized condition, in the unoxidized condition, the non-nodal design has a almost 100 times lower elastic modulus compared to the nodal design. Now this is, I've not shown that graph here, because the graph I've shown here is in the oxidized condition. But even in the oxidized condition, you see at least about a 20 to 30 gigapascal lower elastic modulus in the non-nodal design compared to the nodal design. So therefore, by using the out of plane elastic modulus flexure approach, you can then devise a test whereby you can qualify the non-nodal design as a more preferable support structure design compared to the nodal design. Did was looked at some 4-point bend tests. So if you remember, like I said, in service, what you actually have, you got thermomechanical fatigue, you got a temperature gradient across the hook to the hot gas wash surface. So because of this temperature gradient, the material flattens and unflattens in service. So what we did was, rather than doing a thermomechanical test at high temperatures, we tried to do the same thing but at room temperature. So rather than depending on a temperature gradient, we actually applied a load. So the flattening and unflattening at room temperature was produced by a 4-point bend test approach. So we produce the same effect of flattening and unflattening, but rather than depending on a temperature gradient, we did the same thing by applying a load. In a way to try to understand, what are the failure responses of a nodal versus a non-nodal design. So typically we had a test piece where we had, the abradable sitting. We applied a load under 4-point. So you've got the 4-point, loading rollers that apply a load on the upper surface and causing this this specimen to flatten and unflatten as the load is applied and then removed. So what we did was we did a series of tests on the nodal and the non-nodal design. We typically applied increasing displacements at the loading rollers, going from 0 to about 1.5 millimeters and up to about 40,000 cycles. You can keep doing this to higher and higher number of cycles, but as far as the test that we did, we got the response that we needed to get after 40,000 cycles. We did interrupted tests. So basically what we did was we did a series of tests. I mean, we applied a certain displacement, did a number of flexural cycles, typically of the order of 10,000, take the specimen out, inspect the specimen for cracks, put the specimen back in again, and then repeat it, and then go to increasing the higher number of cycles at a given displacement. So we did a number of tests. So if you can see what I've done here, I've plotted the elastic modulus that we have measured in the interrupted test over a number of cycles. The displacements indicated here are really the displacement that we applied. So we went from around 0.4 to about 1.4 millimeters or 1.2 or 1.4 millimeters. And basically what you can see is that when the failure of the abradable occurs in the nodal design, there's a sudden drop in the elastic modulus. So as long as there is no real damage being accumulated within the abradable, the elastic modulus is more or less constant. But beyond a certain displacement or beyond a certain number of cycles, when the abradable begins to develop cracks and begins to crack, then there is a sudden drop in the elastic modulus. So in a way, you can actually ascertain the number of cycles for a given displacement or the displacement for a given number of cycles when the abradable begins to fail. If we look at the corresponding change in shape of the abradable, like I said, we did these interrupted tests. So effectively, you do a number of cycles, take the specimen out, you measure the shape of the specimen, you measure the elastic modulus using resonance, you inspect the side walls, then put the test piece back again, do a few more thousand number of cycles, again, take it out and repeat the procedure. What you can see is that after an initial relaxation that occurs because of the removal of residual stresses, if you look at the non-nodal design where you do not have any K nodes and X nodes, you do not see any more change in shape, even though the number of cycles go from 10,000 to about 40,000. But on the other hand, in the case of the nodal design, where cracking is occurring at the nodes, the K and the X nodes, you see a gradual flattening or permanent deformation of the abradable. So as the number of cracks form and begin to grow, you get permanent deformation and therefore a permanent change in shape. And there's a sudden change in shape that occurs, which corresponds to a sudden drop in the elastic modulus. So in many ways, what we did was we were able to identify a failure criterion for these abradables. So the failure criterion was based on a dramatic change in the shape, which was accompanied by a sudden drop in the elastic modulus. So again, using a cyclic flexure and by using a 4-point bend test as well as a using resonance methods, we were able to actually down select a non-nodal abradable design from a nodal design in terms of increasing the life of the abradable on the segment. So these are two two very broad topics that I wanted to share with you. One of them is based on repair, how you can actually put a segment back in service by repairing it, and how you can actually qualify the repair, both in terms of quantitative method as well as actually changing the design dramatically from the pre-existing design to another design. And the other one is looking at kind of single crystal applications of a turbine blade where you can use where you can use miniature testing to come up with to come up with a set of constitutive equations that you can use in process modeling to account for the evolution of plastic strain and stress that you can use then as kind of criteria functions. There are also other research topics that we are looking at in the turbine aerofoil materials space. One of them being the formation of secondary grains during casting. So like I said, here we looked at the formation of secondary grains or recrystallization following heat treatment, but there's also secondary grains that form during casting itself, even before you heat treat. So there's a significant package of work that's looking at the mechanism for the formation of these grains during casting itself. We're also looking at using in situ methods based on miniature testing to track recovery and recrystallization. So whilst you saw in one of the things I showed you, one of the topics I showed you where we were looking at developing constitutive equations, another method is actually trying to track recrystallization from the change in the resistance. So in other words, an in situ method of tracking recovery and recrystallization during heat treatment. There's some work that I've done recently looking at the evolution of precipitates and dissolution of precipitates during disc alloys, during processing of disc alloys. So in other words, this is not single crystal materials per se, but the same concepts can also be used in single crystal materials, effectively looking at resistance-based methods in quantifying phase transformations. This work has been recently published in metallurgical transactions. There's also some work that I've been doing that's looking at laser powder bed. I've not shared this work with you, but that's mainly looking at alloy development, developing high temperature alloys typically at about, for 1,000-degree applications with a view towards mitigating strain age cracking. This is some ongoing work with the, with the additive team in services. There's also some work that we're doing looking at materials beyond nickel-based alloys. So like I said, nickel-based alloys have kind of reached, reached their boundary of applications. So there is some work looking at more speculative materials like, high entropy alloys or refractory metal alloys, such as niobium silicon based alloys, looking at, where you can get higher temperature creep. But of course, that comes at a deficit for things like, for example, ductility, or say, for example, oxidation. And again, there's a lot of work that's being focused on developing technologies where you get more innovative manufacturing methods to develop internal cooling configurations. So like I said, one of the main emphasis within the manufacturing space is looking at methods of manufacture where you can get intricate cooling passages, still using investment casting, but kind of some form of modification of investment casting processes. So that's again, a big body of work that's looking at how we can get intricate cooling configurations, either during using additive manufacturing or using traditional investment casting, but slightly novel methodologies therein. So that's really what I wanted to share with you. I must have probably slightly overshot my 1 hour, but yeah, happy to take any questions if we have time for questions.
Thanks, Neil, for wonderful presentation. I hope there will be questions. Anyone? Yeah, Carl.
Hi, Neil. Thanks a lot for that. I just wondered, I know this may be an unfair question. Where do you, there's an echo somewhere?
Yeah.
Okay. Where do you see the changes coming in about the electrification for aerospace? Do you think this is going to cause wholesale changes to the materials that we use? Is it obviously going to come with a redesign, but is it more of a same as what we're using now, but just obviously different sort of oomph at the back, or is it going to completely redesign and ask different questions of the materials that we use?
So there are a bunch of people, Carl, in the what do you call them, central technology team that are looking at this. I'm kind of lesser, kind of further away from it, but they have looked at batteries, kind of development of work looking at developing batteries. In terms of materials, there is work going on in materials. It probably would be going away from traditional kind of nickel-based alloys. I would envisage. It's probably going towards, I wouldn't say actually non-metallics, but it's probably would be a kind of sidestepping from nickel alloys. There is a lot of work going on in this space. I'm kind of not probably at liberty to say much more, but have you heard of Neil Glover from Rolls-Royce?
Yes.
So Neil Glover is one of the main architects of this. So he leads the central technology team. Neil Glover is very heavily involved in the electrification aspect of this, and in addition, other looking at alloy development in general. But that's one of Neil Glover's main jobs is electrification.
Yeah, so I'm part of the Future of E-Machine hub in Sheffield, and I know Rolls-Royce have got a really strong presence there. At the moment, they've really been kind of focusing on showing the kind of the cobalt ions, but for the actual energy electricity generation side of the electric motor, rather than the, we'll still have to have turbines and still have to be spinning something very, very fast. I was just wondering whether there's been I'm sure there has, but what the calculation is in terms of predicting the temperatures at which we'll be needing the materials to operate at. I'm assuming they're probably going to be quite a lot lower, and whether that selfishly, I'm just wondering whether that could shift it back towards steel rather than nickel in terms of not quite requiring the high temperature strength as what we demand of nickel now.
Yeah, no, like I say, it's a good question. I'm probably less qualified, to say much more on that. But
That's fine. Yeah.
but I mean, you're right. I mean, one of the things has been, it might not be an entirely electrification project. You might still have, you might still have aspects of the turbine still there. It may be kind of a hybrid between, the conventional gas turbine. So not when I say conventional, not conventional, but it probably, just having pure electrification, that maybe a bit more in the distant future.
Sure. Excellent. Well, I really enjoyed your presentation. Thank you very much.
Oh, thank you.
Thanks. Any other questions? Jeff?
I think Jeff's had to go.
Okay.
I think he had another meeting at 2.
Yeah. So Neil, do you think already a lot of research happening in the area of high entropy alloys to replace maybe nickel alloys? How is the status?
So there is, so I'll probably put it this way, Prakash, is that there's a lot of work going on and in fact, they do have beyond nickel-based super alloys conferences. I think it's every 4 years. There was one in Japan, I think I think it was just pre-COVID, I think maybe 2019, and there was one I think in Oxford that preceded it. So there is a lot of work going on in high entropy alloys, in refractory metal alloys, etc. But there's a couple of important things. The first thing is these alloys are generally very good in a couple of properties, but they're absolutely abysmal in other things. So, if you look at, for example, niobium silicon, it's got excellent creep properties, and they'll probably shout, the people who kind of advocate it will say, oh, creep is the best. But then the problem is its room temperature ductility is awful, and so is its oxidation strength. So the one thing about nickel is that it's one of the, very, I would say, unique metals where in terms of high temperature application, it embodies good strength, good ductility, good oxidation in the sense that if you alloy it with aluminium, etc., you can form a alumina scale. So it's kind of, I won't say ubiquitous, but it's a remarkable metal that one will find very hard to replace. So that's one aspect of it. The other aspect of it is that you might design these alloys, but manufacturing them would be a very big challenge. So whilst you can probably make arc melt buttons, etc., to actually make a blade would present a very big challenge. And I think it's probably fair to say that manufacturing methods have not gone hand in hand with development of the alloy per se, like they did in nickel-based alloys. Manufacturing very often dictated the type of nickel alloy that you would use, as opposed to in these other systems where people have just looked at, making small little arc melts and small specimens rather than scaling up.
Yeah, like bulk metallic glasses.
Yeah.
So when we scale it up to big industrial applications, it may not perform in all the properties wise or something, right?
Yeah, you might not have a cost-effective way of making a number of them. So in other words, I think the analogous case is in case of 4th generation nickel-based alloys. They are, they're wonderful, but the problem is the cost of ruthenium. Literally has kicked them out of the door because it's not sustainable. So one can put forth an argument here is that whilst these alloys have got remarkable properties, it may cost an arm and a length to make them to make a viable manufacturing method to produce them, to make tens and thousands of castings or some such turbine components. But the jury's out. I mean, like I say, I might be talking a bit more prematurely, but as it stands, I would probably say that manufacturing is way behind materials in this domain.
So do you think iron-based alloys or cobalt-based may come close to nickel-based alloys with, you know, uh, close to nickel alloys to perform in equal way or better with more research in those type of alloys?
Yeah, so cobalt-based alloys have been, so there's a lot of work on cobalt-based alloys led by Dave Dye from Imperial. So they've got this COAl3W, kind of gamma prime type phase, but from, using cobalt rather than Ni3Al. So they have shown that, you get a kind of ordered phase in these cobalt-based alloys that one can use. And there was a lot of work being touted in the disc alloy space, not so much in the blade space, but more in the disc space. So the like 650, 700 degree application. Can we use cobalt-based alloys instead of nickel-based alloys? So far, it's not seen the light of day. I think again they must be having issues that, very good in something but pretty poor in something else. But yes, cobalt-based alloys have progressed. Your other question, there's also been work done on Laves phase alloys. Ian Baumick from Cambridge, who worked with Howard, he did a PhD on Laves phase based alloys. Again, the application was more on statics, on segments,
Okay.
but oxidation was another issue on those alloys.
Okay, thank you. Thank you very much. Any questions from anyone? Okay, if no more questions, I would like to once again thank Neil for your time and accepting our invitation to give the talk, and it was wonderful. Thank you so much.
Yeah, it's my pleasure.
Yeah, okay, see you all. Bye-bye.
Bye-bye.
Oh, Jeff is there. Okay. Jeff, you want to say something? Okay.
I was just going to say hi to Neil, but
did he leave? Left, I think. Right? Oh, okay.
Okay.
No, I asked after his presentation, Jeff, are you there?
I had to dip out for 15 minutes.
Okay.
But then I came back.
Okay. Yeah.
I'll catch it on rerun.
Yeah.